Welcome back to Physics 192. I'm Gerard Blanchard. Last time we introduced the concept of electrical power, and specifically electrical power is related to the voltage across an electrical component and the current through that electrical component by the equation power is equal to voltage times current. Let's put that to work in some examples. What is the power dissipated by the resistor in this circuit if the EMF in the battery is 2 volts? The resistance is unknown, but we are told that the current in the circuit is 2 amperes. Okay, here's our battery, positive side over here. We're told that the EMF of the battery is 2 volts. We have a resistor, R, and we are told that the current in the circuit, I, is equal to 2 amperes, and we are asked for the power that is dissipated by the resistor. So that's what we're looking for. We do know that the power dissipated by the resistor is the voltage difference across the resistor times the current. So delta V times I. Well, we know I is 2 amperes. What is the voltage difference across the resistor? And I'll mark that as delta V R, so that we know that we're looking for the change in voltage across the resistor. Well, you might intuit that it's 2 volts, and you would be correct. Let's show that using our equations. Let's use our Kirchhoff's voltage law. Starting from here and going around. Going from here, we're going positive 2 volts. So delta V total is equal to 0. So our first step going here would be plus 2 volts. And then we have the voltage change across the resistor. We're going with the current, so we're going down voltage. So that would be minus delta V across the resistor, and then we're back where we started, so it has to equal 0. So by adding delta V resistor to both sides, we see that 2 is equal to delta V resistor. So, as I said, as you might have intuited, the voltage change across the resistor has to be 2 volts, and so the power dissipated by the resistor is simply 2 times the current through the resistor, which is also 2, or the power dissipated is 4, and 4 basic metric units of power, which are watts. So the power dissipated by that resistor is 4 watts. And that's what we were asked for. Let's work another example. How much work are the batteries in this circuit doing in every 10-second time interval? Now, since we have work and time, that suggests power, because remember that power is equal to work done divided by time. So draw your diagram, list all your knowns and unknowns, and get started on that question, please. Okay, We have a 2-volt battery here. That's a positive side. And we have a 2-volt battery there. That's the positive side. And then we have a resistor, a 2 ohm resistor. And I'm going to assume that that current is going to flow around like this. And we don't know what the current is. We're asked for the work done by the batteries in 10 seconds. So the work done by the batteries in 10 seconds, we don't know that, but what we do know is that power is equal to work done divided by the time over which the work is done. So power is equal to work divided by the change in time. So the work done by a battery will be equal to the power in each battery times the change in time. So in order to find out the work done by each battery, we need to find the power delivered by each battery and then multiply by time. Delta T is equal to 10 seconds. So 10 seconds is equal to delta T. Okay. Well, power is also equal to change in voltage times current. So for power, I can write the change in voltage times current times change in time is equal to the work done. So what I really have to figure out is the current. I know delta T, I know the change in voltage across each battery, so I need to figure out the current in the circuit. How do we do that? We use our Kirchhoff's voltage law. Delta V total is equal to 0. So I'll start right here. Okay, I'm going to go up voltage 2 volts, up voltage 2 volts, so that'd be plus 2, and then I'll go around. Now I'm going across this resistor with the current, so I'm going down voltage, so that'd be minus 2 times I is equal to 0. So that says that 4 minus 2I is equal to 0. Or 4 is equal to 2I, where I've added 2I to both sides. Or 2 amperes is equal to I. So the current is 2 amperes. So the power delivered by each battery, and I'll do each battery separately. Each battery is 2 volts. So for one battery, we have a delta V of 2 volts times a current of 2 amperes times a change in time of 10 seconds, and those are all basic metric units, volts, amperes, and seconds, is equal to the work done by an individual battery. So that would be 2 times 2 times 10 is 40. So 40 units of work were done. And our basic metric unit of work is our basic metric unit of energy. So that'd be 40 joules. So each battery does 40 joules of work in a 10-second interval. So in total, the batteries do 80 joules of work in a 10-second interval. Now, what kind of work are these batteries doing? What they're doing is they're pushing electrons against electrostatic repulsion. They're pushing electrons from the positive anode to the negative anode. So, to the negative cathode, I mean. They're pushing electrons from the positive anode to the negative cathode. So there are already electrons at the cathode, but the chemical reactions of the battery are pushing additional electrons to the cathode against the repulsion of the electrons that are already there. So that is the work done by the batteries. So the batteries are acting as pumps of electrical charge. They're moving negative charge from the positive anode to the cathode, and they're effectively moving positive charge from the cathode to the anode. So they are separating electric charge, which takes work, and that is what the batteries are doing. Let's do another example. In the circuit below, if R1 is equal to 10 ohms and R2 is equal to 15 ohms, how much power is dissipated in R2? So please draw your diagram. And since we're looking for the power dissipated in R2, we'll eventually have to figure out the current through R2 and the voltage difference across R2, since power is equal to voltage difference times current. So please get started on that. Okay, let's draw our diagram. Here's our 24 volt battery. And then we have a 15 ohm resistor here, a 20 ohm resistor here, and in between we have R2 is equal to 15 ohms. Then we have another resistor over here, which is 30 ohms. And then we have a resistor here, which is R1, which is 10 ohms. And let me draw out the currents. I'll call this I1. And then through R2, I'll have I2. And then over here, I'll have I3. And we are looking for the power across R2. And I'm just going to call that P2, just to keep things simple. The power across R2 is what we're looking for. We know that the power across R2 is going to be equal to the change in voltage across R2, and I'll just write that as delta V2, times the current through R2, which is I2. And we also know that the change in voltage across R2 is going to be equal to R2 times the current. So power dissipated by R2 is equal to R2 times the current through R2. So that's delta V2, and then we still multiply by I2. So the power dissipated by R2 is going to be equal to R2 times I2 squared. We know R2, power 2, is equal to 15 times I2 squared. So what we have to figure out is I2. Okay, we know how to do that. We use our Kirchhoff's laws. The first would be that I1 is equal to I2 plus I3. Okay, because I1 comes into this point and it splits off into I2 and I3. Our second law that we're going to use would be our Kirchhoff's voltage law. So that would be delta V total is equal to 0, meaning that the change in voltage when we go around any loop is going to be 0. So I'll start here and I'll go around this loop in that way. So first I'm going across R2 with the current, so I'm going down voltage, so that would be minus 15 I2. And then I'm going across the 10 ohm resistor in the direction of I1. So I'm still going down voltage, so it'd be minus 10 I1. Then I'm stepping up, I'm going up voltage across the battery, so that'd be plus 24. And then minus 15 I1. And that has to equal 0. We can simplify that a little bit. We can gather these two terms here, where we have minus 10 I1 and minus 15 I1. So that'd be minus 25 I1. Then we still have minus 15 I2 plus 24 is equal to 0. Okay, so at this point, we've got one equation with two unknowns. I can eliminate I1 in favor of I3 to make this an equation in terms of I2 and I3. And why would I want to do that? Well, in my second Kirchhoff's voltage law, when I go around this circuit, I'm going to have an equation with I2 and I3. Let me go ahead and do that so that you can see that. Let me do my second. Delta V total is equal to 0. And I'll go around this loop right here in this direction. I'm going with I2. I'm going with I2 across R2, so I'm going with the current down voltage, so it'd be minus 15 I2. And now I'm going across this 30 ohm resistor against I3. So I'm going against the current, so I'm going up in voltage. So it'd be plus 30 I3. And then once again, I'm going across this resistor against the current. I'm going against I3, so I'm going up in voltage. So it'd be plus 20 I3 is equal to 0. So once again, minus 15 I2 plus, we have 30 I3 and 20 I3. That gives me 50 I3 is equal to 0. And I will add, well, actually I won't, because I'm going to wait until I get this equation over here before I add anything to this equation right here. Okay, so what we have here is we have three equations and three unknowns. Our three unknowns are I1, I2, and I3. Here's one equation. Here's another equation. Here's another equation. This equation only has I2 and I3 in it, so I'm going to substitute this in for I1 right here, and that'll give me an equation with just I2 and I3 in it. And then I'll have two equations and two unknowns, and I can work that to a solution. So I have minus 25 I1, which is 25 I2 plus I3, minus 15 I2 plus 24 is equal to 0. So I have minus 25 I2, and I also have minus 15 I2. That gives me minus 40 I2. And then I have minus 25 I3. And then plus 24 is equal to 0. And so I have an equation with I2 and I3. And now I'm going to come back over here, and I am going to add 15 I2 to both sides, so that I have 50 I3 is equal to 15 I2. And that tells me that I3, if I divide by 50, is equal to 15 over 50 times I2. And now I can take that. This is I3. I3 is 15 over 50 times I2. I can take that and substitute it in for I3 right here. And I have minus 40 I2 minus 25 times 15 over 50 I2 plus 24 is equal to 0. Okay, so that'd be minus 40 I2 minus, well, 25 divided by 50 is a half, and a half of 15 is 7.5. So minus 40 I2 minus 7.5 I2 plus 24 is equal to 0, or minus 47.5 I2 plus 24 is equal to 0. I'll add 47.5 I2 to both sides, and I have 24 is equal to 47.5 I2. And so I have 24 divided by 47.5 is equal to I2. And what is 27 divided by 47? 24 divided by 47.5. That would be 0.505 amperes is equal to I2. And now that I know I2, I can use this equation right here to find the power dissipated by the resistor 2. So power 2 is equal to 15 I2 squared, or the power dissipated by resistor 2 is 15 times 0.505 squared, or power is 15 times 0.505 squared. That would be 3.84. 3.84 units of power, which are watts. So the power dissipated by resistor 2 is 3.84 watts, and that is what we were asked to find. To wrap up the topic of circuits with batteries and resistors, we're going to talk about the concept of equivalent resistance. And what that means is that any combination of resistors can be reduced to a single equivalent resistor, meaning a single resistor that has an equivalent resistance to the combination of resistors. Let's take a look at how that's done. Resistors in series are equivalent to a single resistor whose resistance is R equivalent equals the resistance of resistor 1 plus the resistance of resistor 2 plus the resistance of however many resistors you have in series. Now, what does it mean for resistors to be in series? Let's take a look at this circuit. We have a 1.5 volt battery, a 1 ohm resistor connected to a 2 ohm resistor, connected to a 3 ohm resistor, and there are no branches in between the resistors. So, whatever current goes through the 1 ohm resistor must also go through the 2 ohm resistor, and the same current must go through the 3 ohm resistor. So there is only one current going through all three of those resistors. So those resistors are in series. Remember, when resistors are in series, there are no branches between the resistors, so that whatever current goes through one must go through the other. So that can be replaced by those three resistors can be replaced by a single equivalent resistor whose resistance is 1 ohm plus 2 ohms plus 3 ohms, or 6 ohms. So the equivalent resistance to those three resistors is a single 6 ohm resistor. Let's show why that is the case. Let me draw that circuit. I have a 1.5 volt battery. There's the positive side up here. And then I have a 1 ohm resistor, a 2 ohm resistor, and a 3 ohm resistor. And then I have an unknown current I flowing through them. Let's take a look at our Kirchhoff's voltage law. Delta V total is equal to 0. If I start from this point, go across the battery, that would be plus 1.5. And then I'm going across this resistor, the 1 ohm resistor, with the current, so it would be minus 1 times I, and then minus 2 times I, and then minus 3 times I, and that is equal to 0. And that is the same as 1.5 minus, I have minus 1I, minus 2I, minus 3I, so it would be 1 plus 2 plus 3 times I equals 0. So I have plus 1.5 and then minus 6I, where 6 is the sum of the resistance of the three resistors. So that's the same as if there were a single 6 ohm resistor there. So plus 1.5 minus 6I is equal to 0 is the same equation we would get if we had this circuit right here. 1.5 R equivalent is equal to 1 plus 2 plus 3. R equivalent is equal to 6. So Kirchhoff's voltage law for this circuit is plus 1.5 minus 6I equals 0. So the Kirchhoff's voltage law is exactly the same for this circuit with the 6 ohm resistor as it is for this circuit with a 1 and a 2 and a 3. So we would get the same equation in both cases. So if these circuits obey the same equation, then they are equivalent. So R equivalent for resistors in series is resistor 1 plus resistor 2 plus resistor 3, and so on. However many resistors you have. We could have had more resistors and it would have worked out the same. So those are resistors in series. The other elementary case for combining resistors are resistors in parallel. Now when resistors are in parallel, they are equivalent to a single resistor with resistance given by this equation. 1 divided by the equivalent resistance is equal to 1 divided by resistor 1 plus 1 divided by resistor 2, and so on. What does it mean for resistors to be in parallel? When resistors are in parallel, that means that the current has different paths that it can flow through, and each path has only one resistor on that path. Let's take a look at this diagram. Here you have a 1.5 volt battery, and you have a 1 ohm, a 2 ohm, and a 3 ohm resistor connected to the battery as shown. Now the current leaving through the battery can flow through either the 1 ohm resistor or the 2 ohm resistor or the 3 ohm resistor and then back to the battery. So from the top of the battery to the bottom of the battery, there are 3 paths that the current can flow on, and each path has only 1 resistor on the path. And in that case, those 3 resistors can be replaced by an equivalent resistor, where we would calculate the equivalent resistance from 1 over resistance equivalent is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. Let's take a look at why that is. Here's my 1.5 volt battery. Here's the positive side. And I have a 1 ohm resistor, a 2 ohm resistor, and a 3 ohm resistor. And let's call this current I1, and this current I2, and this current I3. So I3 flows here. So at this point, we must have a current going into this point that's equal to I2 plus I3. So I'm just going to write I2 plus I3. And at this point, we must have a current flowing in that's equal to I1 plus I2 plus I3. So the current coming out of the battery is I1 plus I2 plus I3. Let's figure out what that current is. We're going to figure out that current using our Kirchhoff's voltage law 3 times. And I'm going to start, in each case, I'm going to start right here at the bottom. And I'm going to go up across the battery. And then one time I'm going to go across the 1 ohm resistor. The second time I'm going to go across the 2 ohm resistor. And the third time I'm going to go across the 3 ohm resistor. So let's do that. Delta V total is equal to 0. So in the first case, I've got plus 1.5. And then minus 1 I1 is equal to 0. Or that tells me that 1.5 is equal to 1 I1, or 1.5 divided by 1 is equal to I1. And I'm going to leave that divided by 1 there so that to make clear what's going to come afterwards. In the second case, we have delta V total is equal to 0. And for the second loop, I'm going to go up across this resistor, across this battery, so plus 1.5. And then I'm going to go along these conductors and down across resistor 2. So it'd be minus 2 I2 is equal to 0. So that gives us 1.5 is equal to 2 I2, or 1.5 divided by 2 is equal to I2. And then the third time we have delta V total is equal to 0. For the third one, I'm going to go up across this battery, so plus 1.5. And then I'm going to go down across R3, or the 3 ohm resistor, and back. So it'd be minus 3 I3 is equal to 0, or 1.5 is equal to 3 I3, or 1.5 divided by 3 is equal to I3. And the total current from the battery, we'll call that I. We'll say that I is equal to the current from the battery. I is equal to I1 plus I2 plus I3. So that is I is equal to 1.5 divided by 1 plus 1.5 divided by 2 for I2. 1.5 divided by 1 is I1. 1.5 divided by 2 is I2, plus 1.5 divided by 3 for I3. And I have a 1.5 in common here, so I can factor that out. So I is equal to 1.5 times 1 over 1 plus 1 over 2 plus 1 over 3. Now that is the same equation that we would get if we had a single battery, 1.5 volts, and a single resistor, R equivalent. There's our current I. And so our Kirchhoff's voltage law here would be plus 1.5. So delta V total is equal to 0. Would be 1.5 minus R equivalent times I, and then back to our starting point equals 0. So 1.5 is equal to R equivalent times I, or 1.5 divided by R equivalent is equal to I. And let me write that as 1.5 times 1 over R equivalent is equal to I. So if these are the same currents, then this I and this I are the same. And so I have 1.5 times 1 over R equivalent is equal to 1.5 times 1 over 1 plus 1 over 2 plus 1 over 3. And dividing through by 1.5 tells me that 1 over R equivalent is equal to 1 over 1 plus 1 over 2 plus 1 over 3. And what is that equal to? 1 over R equivalent is equal to 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3. So that would be 1.83. And that tells me that R equivalent would be 1 over 1.83. And that's equal to 1 divided by 1.83. That would be 0.546. 0.546 ohms is the equivalent resistance to those 3 resistors in parallel. So you can see two things here. One is where our equation for equivalent resistance for resistors in parallel comes from. 1 over R equivalent is 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance. And the second thing that you see is that the equivalent resistance is actually less than the resistance of any of the resistors that are in parallel. And the reason why that is that by giving the current more paths to flow through, we actually decrease the resistance to current flow. So equivalent resistance is less than the resistance of the individual resistors when they are in parallel. And the contrary is true for resistors in series. Resistors in series always add up and present a greater total resistance than the resistance of the individual components. Now this procedure can be used for any circuit consisting of one battery and any number of resistors. Let's take a look at an example of that. Here we have a circuit with a 1.5 volt battery, and we have a 2 ohm resistor, a 1 ohm resistor, a couple of 2 ohm resistors connected as shown. And this whole configuration of resistors is actually equivalent to a single 1 ohm resistor as shown in the circuit to the right. Let's take a look at how we arrive at that. Let's draw our circuit. We have 1.5 volts, and then we have a 2 ohm resistor and a 1 ohm resistor and a 2 ohm resistor and a 2 ohm resistor. Okay, let's see what we can do with that. We'll start from the battery, and we have a current flowing along this wire, and then it branches out. It goes across the 2 ohm resistor, and then it goes across all of these resistors and meets up with the current through the 2 ohm resistor again. So in some sense, this 2 ohm resistor is in parallel with all of these resistors taken together. But we can't use our equivalent resistance equation yet, because we don't have while we have a single resistance here, we don't have a single resistance for all of this. Let's take a look at the 1 ohm resistor and the 2 ohm resistors. A current flows through the 1 ohm resistor, then it flows through this 2 ohm resistor, but it also flows through this 2 ohm resistor. So we can't, so in some sense, this 1 ohm resistor and these 2 ohm resistors are in series, but we can't use our equation because not all of the current that flows through the 1 ohm resistor flows through this 2 ohm resistor, flows through this 2 ohm resistor, or flows through this 2 ohm resistor. Now these 2 ohm resistors, however, are in parallel. If I look at this point right here and this point right here, then whatever current flows in here flows through this 2 ohm resistor or flows through this 2 ohm resistor. So here we have 2 resistors that are in parallel. The current can take 2 paths, and each time it only flows through 1 resistor. So what we can do is we can replace those 2 resistors with a single resistor. 1.5 volt battery, a 2 ohm resistor, a 1 ohm resistor, and I'll call this R equivalent 1. So our first equivalent resistance. So I can replace these 2 resistors in parallel with a single resistor. And my equation would be 1 over R equivalent 1 is equal to 1 over 2 plus 1 over 2, or 1 over R equivalent 1 is equal to 1, or R equivalent 1 is equal to 1 over 1, which is 1. So this equivalent resistor, so R equivalent 1 is equal to 1. So this resistor here, this equivalent resistor, is a 1 ohm resistor. Now I do have 2 resistors in series here. Whatever current goes through resistor 1 must go through resistance equivalent, or resistor equivalent 1. So these 2 are in series. So I can replace this circuit with another circuit where I have a 1.5 volt battery, a 2 ohm resistor here, and I'll call that R equivalent 2 right here, where R equivalent 2, since these are in series now, is equal to 1 plus 1, or R equivalent 2 is equal to 2. So this equivalent resistor is a 2 ohm resistor. And now I do in fact have 2 resistors in parallel. The current can go through this resistor, or it can go through this resistor, and each time it only goes through one resistor. So I can combine these as parallel resistors. So we get our final equivalent circuit, 1.5 volt battery. We'll replace with R equivalent 3, where 1 over R equivalent 3 is equal to 1 over 2 plus 1 over 2, because these are each 2 ohm resistors, or 1 over R equivalent 3 is equal to 1, or R equivalent 3 is 1 over 1, or R equivalent 3 is 1. So all of these are equivalent circuits. This, and this are all equivalent circuits. So in this case, we replace 2 resistors in parallel with a single one. 2 resistors in series make a single equivalent resistor, and then 2 resistors in parallel make a single resistor. So all 4 of these circuits here are equivalent circuits. We'll do an example using equivalent circuits next time. Until then, think physics.